In this tutorial, I'll show you how to sketch rational functions. The question reads, sketch the graph of the function shown underneath. Notice that the function that we're working with is a fraction, and we have a polynomial at the top and one at the bottom. And that by definition is a rational function. To do this effectively, we'll be going through each of these steps and I'll explain exactly how it's done. For the very first step, we need to find the domain. Now, given that this is a rational function, the domain will be dictated by the restrictions found in the denominator, because the denominator cannot equal to 0. What we have to do is factor this cubic function into factored form, and then from there we can easily solve to see where x cannot be 0. That being said, let's go ahead and factor this cubic. Factoring a cubic requires the use of the rational zero theorem. And for that, we need to identify our constant term, being -12, and our leading coefficient, which is 1. If I find all the factors of my constant, and I call them p, the factors are plus minus 1, plus minus 2, 3, 4, 6, and 12. And I divide all these numbers out by 1, which I'll call q. Normally, if this were a number other than 1, you would use all the factors of that number. But because it's 1, it makes it slightly easier. So I'll divide all of these numbers out by q, and that will give me a potential list of roots for the polynomial underneath only. So dividing out p with q gives me all of these numbers as potential candidates. Next, to find out which of these are actually roots, you have to substitute each of these back into the function found in the denominator. And if the output results into 0, then it is a root for the polynomial. The ones that actually output 0 are -3, +1, and -4. So we can rewrite the denominator as x plus 3, x minus 1, and x plus 4, rather than what you see right here. And setting this to not equal 0, we will find out that x cannot be -3, +1, or -4. Therefore, our domain consists of all x values such that x cannot be -3, +1, and -4. Okay, moving on to step number 2. If g of x, so I'll say that this polynomial is g of x, and this polynomial is h of x. If g of x and h of x have common factors, cancel all common factors, determining the x-coordinates of any removable discontinuities, and rewrite f in lowest terms. Essentially what they're saying is find out the removable discontinuities. And to do that, we need to factor now the numerator as well. And where there are common factors, that will determine a removable discontinuity. That's essentially when you have a hole in the graph. And it's a little bit different than a vertical asymptote as explained in previous videos. So we have to factor this, and rather than showing you all the steps again of factoring this polynomial this time, I'll just tell you what it is. G of x in factored form, take a good look at it, should look like this. And of course, the denominator we found earlier to be what was written above there. So x plus 3, x minus 1, and x plus 4. Notice that this factor right here and this factor are identical. This means that we will have a removable discontinuity when x is -3. So this will cancel out, and that will cancel out. And the function that we'll be working with moving forward is everything but these two. Now to find out exactly where that hole will be, that removable discontinuity, I'll take -3 and substitute it back into my function. If I substitute it back into this function, I'll end up with an output, let me show you, that is equal to -3/2. So the hole will be at -3 and -1.5, which is equivalent to that fraction. This is our hole, or our removable discontinuity. In step number 3, they say check for symmetry. The way you do that is if you substitute -x into the function, and it outputs as negative f of x, then the graph is odd and therefore symmetrical about the origin. In addition, if substituting negative x into the function gives you the function again, so no change, then the graph of f of x is even and therefore symmetrical about the y-axis. Now I tried this myself. I substituted negative x into the function and I did not find this behavior, and I did not find this behavior either. Therefore, it is not symmetrical about the x or y-axis. Let's move on to step number 4. Find the y-intercept by evaluating f at 0. That's not so bad. If we substitute 0 into the original function, that term becomes 0, 0, 0. We end up with negative 18 at the top. That becomes 0, 0, and 0. So we have negative 18 divided by negative 12. That's equal to 3 over 2. Therefore, our y-intercept will be at 0 and positive 3 over 2, which is 1.5. Okay, let's carry on. In step number 5, we have to find the x-intercepts by finding the zeros of the numerator of f, being careful to use the new numerator if a common factor has been removed. Our numerator is right here, and I'll set that equal to 0. If I set this equal to 0, I end up with roots that are at x positive 3 and x being negative 2. And of course, because these are the roots, we would have two brand new points, 3 and 0, and negative 2 and 0. So far we have 4 points, this one, that one, and these two as our x-intercepts. Okay, let's carry on. In step 6, find the vertical asymptotes by finding the zeros of the denominator of f, being careful to use the new denominator. Use test values to determine the behavior of the graph on each side of the vertical asymptotes. So using now the new denominator, if we solve for x, we end up with x values of positive 1 and negative 4. We will have asymptotes at these x values. These are essentially boundaries that the graph will never touch, and to the left and to the right of these 2 points, it will either go to positive or negative infinity. Let's begin to sketch what's happening. We'll have asymptotes at positive 1. So if this is our x-axis, that's our y. We can call this space 1 unit, and it will never pass through this boundary. And at negative 4, we can say that that's negative 4, and another asymptote here. We want to know what happens to the left of negative 4, to the right of negative 4, and the same thing with positive 1, to the left and to the right. To the left of negative 4, as we approach the asymptote, it becomes more and more positive, infinitely. So expect it to go like this, closer to negative 4. To the right of negative 4, so choosing a value like negative 3.99, it gets infinitely negative. So expect it to go like this. To the left of 1, the graph approaches positive infinity. So as you go this way, it becomes more and more positive. And if you pick a value that's a little more positive than 1, you get negative infinity. So the closer you get, the more negative it becomes. Okay, let's move on to the next step. Determine whether the graph has any horizontal or slant asymptotes. Remember what determines horizontal asymptotes. That's if the denominator degree is higher than that of the numerator. In this case, they're both the same. So what you do is you take the coefficient of the highest degree here and the coefficient of the highest degree here and divide them. And dividing 1 by 1 gives you 1. So we should have a horizontal asymptote where y is equal to 1. Let me mark that down here. Another thing to mention, we will not have any slant asymptotes because the highest degrees are equal. In step number 8, we have to plot points choosing values of x between each intercept and values of x on either side of all vertical asymptotes. Before we do that, let me go ahead and plot these points that I found earlier. Negative 3 and negative 1.5 was a whole or a removable discontinuity. Negative 3 should be somewhere here, and negative 1.5 we can say is right there. So there should be a hole as shown right here. Furthermore, the point 0 and 1.5 was a y-intercept. So 0 and 1.5 is right here. Expect this to pass through there. If I select a point like negative 5 and place it into the function, I'll get positive 4. So negative 5 and 4 is up here. If I place half into the function, you should end up with around 2.7. So half and 2.7 is right there. Substituting 2 into the function gives us negative 0.6 repeating. So that's 2. Negative 0.6 should be here. Our graph, therefore, should look like this. This part of the curve and this part of the curve do not touch the horizontal asymptote, whereas this from here through here minus that part is continuous. And there you have it. That is how to sketch rational functions.